We can start off by just saying our names and introducing ourselves. I'm Derya Akbaba, and I'm a PhD student at.
I'm Sofia Andersson. I'm a PhD student at Lund University.
Markus Fritzche, also from the Clipping University.
I am Xavante Erickson. I'm from Lund University.
I'm Sara Karimi. I'm from KDH University.
Great, and today our project is PlantMap. Sorry, really wanted to do that. Down. I think I need to click screen is included. Okay. So we are going to go through the motivation for our project, talk about the dataset prep methods, results, some conclusions, and future work, kind of your standard overview of a project. You'll notice there are very nice wildflowers. The theme of our project is around wildflowers. There are different variants throughout the slideshow. If you can name them, you might get a prize from Raz. Just kidding. So for our introduction, the motivation for our project actually started, maybe you all remember a month ago when Raz was talking about wildflower composition in Norland. So we're going to generalize this a little bit and talk about why wildflowers are important. They help you understand the ecosystem, its health. They're important for pollinators, and in general, they give you kind of an idea of the natural landscape that you're in. And sort of the hypothesis that we have is if you know the composition of the wildflowers, okay, have some sort of plant map in a field, then it's going to be annoying. Then you can know where and what type of microbial tea that you can add to encourage growth and have complementary plants. You can use this with precision agriculture. All these words are very hard to say. And this is to help with unwanted plants. So there might be some wildflowers that are weeds and you might just not want them. You can, again, optimize pesticide application and time your cattle grazing. And I'm sure there are multiple other applications. You can think about when to go out and have a wonderful photo shoot with your kids picking the most beautiful wildflowers, for example. You can use your imagination. The challenges are, though, that flowers are tiny and they're everywhere. So in order to understand the composition, you have to take an image. And this image is going to have these tiny little flowers and they're going to be sparsely distributed. Also, the composition changes every few weeks. You're not going to have the same looking field all the time. That would be creepy and weird. So it needs to require constant update. And the ML models that we have right now are not super great. Object identification is segmentation and classification are based on single images of flowers, whereas typically wildflowers are in a field and they're small, so they're not already segmented. It also depends on the quality of your imaging equipment. We were lucky to have drone images that were high quality, but maybe our phones aren't so great, especially when you start getting them at weird angles and the lighting is weird, especially when the sun sets at 3 p.m. And then finally, this is going to sort of speak to our project, but there's also issues of privacy. You might not want everyone knowing the composition of your field. So the project goals are to use this ML-powered automation of a data set of raw images, specifically ones that come from Norland, and to segment them and classify them for different flower species, and then to do this in a federated learning way, because the idea is then that different farmers would be able to upload their different images to a federated learning schema and be able to classify and create a composition of their field. And with that, I will hand it over to Sara.
Thank you. Yes, now this. Yes. So as Derya mentioned, our data set was not labeled, so that was one of our tasks to do before we even can do any type of machine learning. We were just provided with images like this, yeah, no labels, no segmentations, no nothing. We just knew that we were introduced with these images and the type of name of this type of the flowers, like maybe just 3-4 of them to look into. So we explored quite a few things in the beginning, also for segmentation and classification, and we they said we were provided 67 images that were taken, were given by Ross, and they were not labeled, and they were from a farm in Norland. So we also looked into this publicly available data set because it's very similar to the data that we are working with. So this actually has 65,000, 200 images of farm fields and wildflowers with labels of the different species of flowers, and also like bounding boxes. So it's like good for object detection and segmentation tasks and classification, of course. The reason why we chose this is that we wanted to first maybe fine-tune whatever model we want to use, so it has already like some capabilities in detecting this, and then we can further fine-tune it for our specific type of images, because we were not given that many samples. Yes, so first we had to, the images were very high resolution. We wanted first break them into smaller chunks. As you can see with smaller, maybe more details, that makes it easier for the models to find flowers, and also like small tiny flowers, and also like it gives us more samples in our training data. And then after that we used we looked into two approaches for labeling and annotating our data set. We used the segmenting model, SAM, that I think it was mentioned last time to first do segmentation on these images to find the segmented masks and the bounding boxes around the images, around the flowers in the image. And then we looked into two approaches to further classify them. One was we used supervised classification, model that you can provide the textual, which is a model that you can provide. I'm looking for Daisy, and then it classifies. And the other one was completely unsupervised, and the other one was explain these two in the future slides. The unsupervised one was like similarity scores. And then eventually using one of these methods, we build the labeled data set. Hugging face, so this is roughly how it looks. We have the bounding boxes and labels of like at least two of the species, and we'll get to that way too in the future slides. And so the methods, it's two parts since this project, as mentioned before, is a federated learning project. We'll go through the ML methods that we use and shortly also the federated part. The ML methods part, we have a supervised segmentation method. Just to shortly describe, this has a huge image encoder, which is trained on everything. Imagine, like gives you an embedding, and some one model actually has a textual prompt input as well, which you can further query. Like encoded image, look for what you want. So for example, that encoder has this image representation of the image, and then combining it with this prompt, textual prompt that comes out of the prompt encoder. It's kind of like a way of querying it, encoded image, and then eventually it gives you different versions of the segmented mask, of course, scores for each, and then usually get as the valid segmentation results. Yes, now the second part.
Yeah, I mean, as you can imagine, let's say we have a lot of images that we want to put them up as six segmentation masks by flower, plus the class labels. So, and all this labeling takes a lot of time. So the question is, can we reduce the work of data preparation? And so we wanted to check some unscore and self methods in order to do so. And one thing we noticed is it doesn't take pre-trained sum, so a segment anything, like pre-trained means like we don't do anything, and it does ask it to give us segmentation masks and bounding boxes of flowers. It's actually pretty good. I mean, as you can see, okay, maybe not because of the resolution, but it's actually doing a decent job to already detect all the images we have there. So we don't have to do actually anything for that. And the only remaining thing are the class labels. I mean, even if we imagine we have 10 million images, we don't have that many, but just imagine, and only two class labels, we still would need to label 10 million images. So what we want to do, I mean, first of all, it's not perfect sum, so we still have a lot of positives. But the advantage what we have is, I mean, if you look closely, they all look pretty green. Like there's no flower visible, and we don't need any deep learning methods, so machine learning methods to filter out these images. I mean, all we need to do is we have some green filter which checks like how's the green ratio of images. And throw them out, and then we have a pretty good segmentation data set. And one method we want to check on was nothing but similarity matching. So it's like pretty simple. Imagine a lot of images and a few amount of classes. So what we want is for each class we take one candidate image. So we only need, for example, 2 classes, we only need to label 2 images and check for every other image how close or what is the closest image to that with some kind of encoder strategy. There's a lot of work about that using rest plus functions and also some your native. What you can try, and the method how it works is as follows: like here's a candidate image, and here is an image to compare to, and we want to expect to have like full then amazing in that case, and allow so for basically every other class. And yeah, we have the pipeline again. So we basically have a vision transformer. We pre-trained it, like what worked best, but optimal was mass and outer model. So we pre-trained that on our data set, and then we can use like this learning method. Where is the problem? Okay, it's not very visible because it's not very visible because loss is basically down at all. Like we tried many different settings. I suspect that the images are just similar. And the only method which actually was a debug run. I run local, loss went down, and if I use the same parameter again, stopped working all of a sudden. So yeah, I think there's a lot of work to do there in the future, but we can abandon this method because it was so hard to train. We focus more on supervised approach instead.
Yes, therefore we include supervised classification. So having the segmentations at hand, we would use something called like a clip model, that is a vision language model. So this model actually is trained with pairs of images and textual descriptions of those images. So you can see that it actually learns that it needs to have a higher correlation in the pairs of images and textual inputs that are more relevant and less correlation in the matrix for the rest of them. So it's actually inclusion contrasting loss. So it looks into like similar and dissimilar samples and has a loss based on that. And eventually it actually learns to give you classes for they provide an image. It has like a text template as input, and eventually it will fill the massive part of that template, and that we can use that one actually as a label of that image. For example, this is the dog image, and the template was a photo of a black, and then it filled the black, so you know there's a dog. And if you give the pre-segmented model, then you have like one image into segments, and the segments are all segments. And as we mentioned before, we wanted to first fine-tune this to some kind of similar data set, because these models are huge and they have been trained on literally everything, so they're not specialized in like wildflower detection. So we took this Einhorn wildflower data set that I mentioned before, the publicly available one, and we further fine-tuned this deep model, the classification bit of our model, with this data set first, before we fine-tune it further with our data set. Our hypothesis was that this will help the model to become a bit more specialized first, and hopefully it should work better with those exercises, and we'll see the results. And now it's the federated part.
So on to the boring stuff, because I assume it's like the majority of people that have done this at this point. So a lot of you might already know it is a way to train with decentralized data. This increases communication efficiency, but the original intent is to increase privacy, of course. The simplest implementation just uses federated average algorithm, basically taking a sample of the total number of clients we want, training it locally, and then taking an average of each of those clients. These can be done locally, can be done arbitrarily in the training. So we have just taken our own training that we've already done, basically putting into federated learning, using the Fed promises of magical implementation for federated learning. So after completion, we basically just take all of the clients to the central server, and aggregate them using federated average or federated added. In the original formulation of federated, they take into account the fraction of data points, something that they get rid of quite quickly in federated add-on, where they only consider the sampled clients instead. After we have collected the clients into a single model, the global model is then redistributed to all the clients, and we repeat the process in trying to train all these clients into the central server again. So of course, we tried both federated average, the original concept, and also the federated add-on to see which one performed best for our purposes. So in sort of short, for federated learning, we avoid sharing data between clients and central server. We decrease the communication overhead by only sharing the weights of all of the clients. We avoid sending all the data to each and every client and central server. Still, this kind of, while it's the best we have at the moment for privacy learning, it's still a hotly debated topic if it is actually private or not, of course. But still, we see that we actually benefit from this kind of learning. So we have effectively decreased the computational for all of the for singular clients. We have used actually distributed beneficially for us. And as I mentioned, we use scale systems, but it's not the best, so to speak. It's supposed to be, we're supposed to have promises that we can have a pre-developed package, which each of the clients can just magically download. They don't have to care about anything. We're just supposed to be able to connect to a central server. And then the scale-out system promises that we organize orchestration, meaning that they don't do any training, but we can just decentralize and tell all of the clients, now you should train, now you should send the data, the client model updates, and then they share some of the statistics, of course. Yes. Results.
Yes. All right, so let's talk about how things actually went when we did all this. So first step, we had to pre-train lift models on the Angular and data set. And we did this in two ways. One way was where we actually tried to classify the data set. So we trained the lift weights and the classifier weights at the same time. Or and then had a different way where we use contrasted loss. Same loss like originally trained with. We used in this case to try to make it to work. So essentially, two different ways of training it: contrastive and categorical. And let's see what happens. So first of all, categorical tip training. Beautiful graph here. That definitely doesn't have any weird overlaps or anything. So as you can see, the train loss goes down. Validation loss goes down, validation accuracy goes up. Great, looks good. But essentially, we had to find these hyperparameters, which we did using Optuna search and RayTune. And it looks pretty decent. We get an accuracy of like 91%, which isn't horrible. And the loss goes down relatively quickly. We don't really see any overfitting. So it looks quite good, and for this we specifically try to maximize the validation accuracy, whereas in the contrastive model we try to optimize for the validation loss, since we didn't really have accuracy there, so we didn't do any explicit classification. So here we see this, the loss goes up and down way more here. You can see the parameters are slightly different, but we do see that the model goes down. It appears that we're something. And what was an issue with the contrastive learning is that the contrastive loss is highly dependent on the batch size. What I found, it felt like the minimum of the loss scaled with the batch size, which made it very difficult to use the hyperparameter tuning in order to find So I just looked at all of the hyperparameter tuning runs and tried to find the one where we actually got the largest decrease in loss, or it looked like the model had learned the most, which happened to be this one. So these two are the models that we will be using in the next step, where we use the actual drone data set. And I'm about to show you a table. Don't be scared. We won't spend a lot of time on this.
We can start off by just
0.001 learning rate, batch size 32, no dropout. And just in the first epoch for the base clip model, we have 66.5%. First epoch with the pre-trained model, we are all the way up to 85%. That's pretty big of a difference. For this part, we actually wanted a model that could learn something within one epoch, as it tends to correlate with max accuracy, but not directly. It's not a linear correlation. We actually use dropout for some of these, but we only use dropout for the contrastive models, which you can see here in the green. We only used, where's the dropout here? We only used the dropout for the contrastive models because we actually saw some evidence of overfitting there. This might also be a scary graph, I just realized, but it's not that scary. So we just basically see that higher learning rate tends to correlate with a better first epoch accuracy. Essentially, that's the case. It's quite interesting. We were supposed to only try 2 parameter combinations per model, but since the contrastive model showed a lot of overfitting very early, that's why we explored more parameters in this case. But essentially what we see is that in the low learning rates especially, it seems that the pre-trained models have way better of a validation accuracy after the first epoch. And if we then go over to federated learning, on behalf of Markus, I want to say that we have these graphs because FedN does not allow you to download the data. So
Yes, but if so, please tell me. I have no idea when export it properly.
yes, we couldn't find it in the documentation, we couldn't find it on the website, so we have to, I do excuse the screenshots, but this says 90 for the training accuracy. And if we follow here, we get up to 94%, which is higher than anything that we actually reached in the on only one machine. And this was done with the best categorically pre-trained models. We actually go up to 94%, which is really interesting that it's actually better. So this is the Fed average. Then if you want to look at the validation results are here for the loss and the accuracy. We also get up to not exactly 94, but very close to 94. So also very interesting that we see an improvement here. And if we then look at FedADAM, slightly different method, we also get up, some models reach 95, some don't, quite close, like 93, 94. We also see this weird wave pattern, not really sure what that means, but we do get slightly higher actually once again. And then if we look here, we only get up to about 92. But that's still in line with the results we achieved on one machine. So it does appear that the FedN is able to achieve comparable and sometimes better results than the one machine model. So we'll move into conclusions.
So just quickly, just the other segmentation. I think the SAM model is pretty good, and we also thought that we had to explore a lot of like the hyperparameters, so that's like one downfall, but overall it's able to adapt after some fine-tuning, able to adapt to our data pretty good. The pre-training on EWD dataset, as Sofia mentioned, it's increased our accuracy compared to the base clip model. Overall, it was on the first epoch accuracy, it gave us a better results, and the federated learning. It improved our results while maintaining the data privacy, but we did not quite like FedN, or maybe that's a strong word, but we think it needs definitely more documentation, more robust operations, and better server looks. It was pretty hard to debug, and also better fault tolerance. We had like random failures without knowing actually what's happening. But I mean, it was a good experience anyways. And quickly, future things to try out. The data set segmentation and annotation. We tried the supervised approach, there are other unsupervised methods to try, which is worth trying out. Just going very quickly over this. And the real world applications, so we think that there's potential for continual learning and human feedback. These data sets could be exposed to humans to give feedback to how the quality was. And also, there's some kind of GUI support would be very nice to actually have this like plant maps showing in pretty UI frameworks for the farmers. And also, test whether the model can be amplified in a way, which is also in line with the UI support. So, thank you very much.
Are there any questions? So how federated did you do it? How many did you run on from your experiments?
Yeah, because we only had 2,000 images and we wanted some test or validation data, we had 6 locals. Everyone has approximately 300, a bit more images. And we didn't want to make it too small.
Yes. So you compared like non-federated setting to federated setting. And I was just wondering, is it exactly the same data in those situations, only that in the federated setting you kind of split it into machines? How do you get higher accuracy?
It's the same validation data, but the training.
Sorry,
go on.
No, for the training data, I mean, of course, that's a bit more biased because every worker has only 300 samples for that. Of course, you get higher scores at the end for the training accuracy.
But for the validation set, they both have the same validation set. So they're both federated and single one. So they use the same validation data set.
But we also trained a bit longer because I'm not sure how you can compare it, but I mean 8 hours with 1 GPU versus we trained I think 6 workers with 1 GPU, but for 5 hours. So we trained a bit longer also.
I have a question.
Yes.
So, I mean, suppose
you want to turn this into some kind of a product, right? So the context is there is quite a lot of funding from the EU in Sweden. That's like from various agencies to help improve rural livelihood. So suppose, I mean, the ideal product would be some kind of app anyone can download, shoot at their field, maybe fly some drones and upload it to some website, and then they get their PlantMap, but they somehow own the data. And whatever product you're developing, maybe there is a, there is some kind of revenue sharing, right? And actual money, I think, will be coming from all these new EU programs for biodiversity, blah, blah, blah. So these are all supposed to be coming. So, I mean, from this project experience, if you were to like say, okay, I want to turn this into a product, how much money would you like to have to say in 1 year want to build a small team? What would your
How much money do you have to offer? Let's see.
I mean, it's in the order of a couple million SEK, right? So these are just tiny startup funds.
I mean,
I think we need some time to think about it.
yeah, exactly. I'm thinking we would need some time. Because there's a lot more that we thought that it's not written in the future works, but we discussed as potential things to try out. And some of those could be related to equipments or could be related to approaches to try or resources, computes, all sorts of things. So yeah.
Can I ask a comment?
Yeah.
If you would make this into a product, would you stick to federated learning or?
Oh, if I would make this into a product, not necessarily. I mean, I think, I would actually just read the regulations from the EU farmer incentive laws, like what would be the way to validate your biodiversity profile. So I would kind of go from that end. But whether it's federated or not, it's a matter of convenience, right? Because if you could have a federation where everyone owns the data and they share their models somehow, it is nicer than centralizing a lot of it, right? So they're two separate problems.
But otherwise, in terms of money, I think we would need some compute time. But I mean, otherwise,
yeah, like you need so many full-time salaries first.
I mean, we were interested in following this for a potential publication. We talked briefly about it, but yeah, we can get back to you on the estimates on stuff.
Well, there was a related paper that actually where we got the pre-training data.
Yeah, it sounded really cool actually. Okay, let's thank them again.